Swayam Prabha. Digital India. Educated India.
And we saw how to compute the AND function. Then OR also can be computed, but XOR cannot be computed. So we also discussed perceptron training algorithm, where we have to do only greater than test. Okay, and very simple algorithm. Whichever vector does not succeed in the test is added to the current weight. So very iterative algorithm. And we saw that if the problem is linearly separable, the perceptron training algorithm has to converge. The convergence proof was also given, which is a very elegant proof, where you consider a function GWN, which from the nature of the expression is bounded, but if the iteration doesn't stop, then the value will become unbounded. So the iteration cannot really continue. This is a proof by contradiction. So now we come to feed-forward network, having looked at perceptron and its. So single perceptron or single neuron cannot compute many useful functions, XOR for example. So in the XOR problem, we need to introduce additional neurons. So the output will be 1. If x1 is 0, x2 is 1, or vice versa. But when both the inputs are same, the output will be 0. So this cannot be computed by a single perceptron because XOR is not a linearly separable function. You cannot separate the 0 class from the 1 class by means of a single hyperplane. Okay, so now we need to introduce additional neurons before the output layer. They are called hidden neurons. They are hidden neurons because they don't directly from the environment, nor do they give out the output to the environment. So this is the nature of feed-forward network. And if we have many layers here, then it will become a deep neural network. Okay. Now, without these hidden layer neurons, XOR cannot be computed. So hidden layer is bringing in the power of computation. So that is the belief with which the deep neural network field has progressed, that as you increase the number of layers, the computation power increases. But this you have to weigh against a very classical result in 1960s, which is due to Kolmogorov. Kolmogorov said that if you have a deep network, if you have a network with multiple layers, then it can be reduced to a single hidden layer neural network where each neuron computes an appropriate function. So the emphasis is on quote unquote appropriate. So Jyotsna, please add a slide to this. So Kolmogorov's result of equivalence of multiple layers neural network to a single hidden layer neural network. And each neuron has to compute an appropriate function. The emphasis is on appropriate, not necessarily the same function. So, so as the number of neurons in the layers and also the number of layers increase, then the neural network can place more and more hyperplanes and thereby have more decision segments available, and thereby the computing power increases. So this is the XOR network. XOR function we can break into two parts. XOR can be computed as x1 bar x12, x1 bar x2 plus x1 x2 bar. Plus means OR. So OR we know can be computed by a single perceptron. So if I have if I'm able to compute x1 bar x2 and x1 x2 bar, both of which are again linearly separable, then the ORing of these two functions will give me XOR. So the hidden layer neurons are actually computing these in a hidden manner. We do not get to see what they're computing, but this is what is happening. Now, a very useful exercise which I have always given whenever I have taught neural network is that you take an XOR network, give the input output values, and keep training the network by iteration on backpropagation algorithm, and then find out what are the functions computed by the hidden layer neurons. So Satyam, you can put this exercise on on the portal on the MS Teams channel, and this exercise is discover what the hidden layer neurons are doing. So again, this is not an assignment but an exercise, but very useful for you to program uh, the backpropagation algorithm and run it on XOR network and study what is there in the hidden layer neurons. What are they computing? So this exercise, Satyam, you can put down, and Jyotsna, you can include this exercise in the slides. So, so this is what is the situation, and we also know that XOR can be computed in another way, where this neuron, one of the neurons, will compute x1 bar plus x2 bar. Another neuron will compute x1 plus x2. So one neuron will compute OR of x1 and x2. Another neuron will compute OR of x1 bar and x2 bar. Now OR of x1 bar plus x2 bar is nothing but a NAND function. Okay, it is x1 x2 bar. So x1 x2 bar is x1 bar plus x2 bar. So NAND function is again computable by a single perceptron. So you can compute OR here and NAND here, and the output neuron will compute AND. Okay, and thereby XOR will be computed. So Jyotsna, again, please give the alternate network for XOR, where you show that one of the hidden layer neurons compute OR, another hidden layer neuron computes NAND function. So for XOR, it is it is easy to find out what the hidden layer neurons are doing. But when it becomes a complex problem, like face recognition, for example, or deciding on loan application, or deciding on visa application, where you may need hidden layer neurons, then it is not easy to find out what the hidden layer neurons are doing. And that's a very interesting question. So is it that for people who apply for visa, one of the neurons in the hidden layer is computing the income level, another is observing the gender of the person, another neuron is observing the educational status? Okay, so is it that they are dividing the work amongst themselves for deciding if a person is visa sanction worthy? So you see here how the hidden layer neurons have arranged between themselves to compute x1 x2 bar and x1 bar x2, or they would compute OR of x1 x2 or NAND of x1 x2. So it is as if the hidden layer neurons are discussing amongst themselves what to compute and send to the next layer. Now this has good correspondence with NLP. So I give the raw text in the input layer. Maybe one layer, the next layer computes the morphology functions. The next to next layer, the part of speech tagging functions. Next to next layer, named entities are detected. So each layer of the neural network is doing some NLP task, and finally the problem specific decision arrives at the output layer. Maybe you're deciding the sentiment of the document or the translation of the text. Okay, so this is how the computation progresses, and the hidden layer neurons do something very intriguing, I would say. Now, so also, Jyotsna, again, please introduce a multi-layer neural network, saying that the first layer does morphology, second layer does pause tagging, third layer does named entity, and so on, just as an indicative diagram. Now, so can we use perceptron training algorithm for training feed-forward neural network? No, because perceptron training algorithm is a supervised learning algorithm. So are you people observing, can we use PTA for training FFN? Are you observing that slide?
Yes, sir, we are.
Okay. So perceptron training algorithm requires labeling of the data. Okay, 0, 0, 0, 0, 1, 1, and so on. So if a neuron has to compute by perceptron training algorithm, then the output for that neuron for the input has to be known. Now see that in hidden layer neurons, I do not have the label specified. When I input 0, 0, I only know the label at the outermost layer. I do not know the label for the hidden layer neurons. So if I do not know the label, how will I run the perceptron training algorithm? Because perceptron training algorithm demands that the failed vector should be added to the weight. How do you know failure or success unless you have the label? Okay. So since you do not have values at the hidden layer neurons, the perceptron training algorithm cannot be used for multi-layer feed-forward network. Okay, multi-layer feed-forward networks are neurons which have the neural network which has multiple layers. Except for output layer, the values are not known for the hidden layers. So now we introduce a technique called gradient descent technique, which is an iterative algorithm for fixing the weight values of the neural network. Okay, again, I'll remind you that in perceptron training algorithm, we would add the failed vector to the weight vector and thereby change the weight values. In feed-forward network, I again have to change the weight values so that the error at the outermost layer is minimized. Okay, how do I arrange to incorporate this change? By how much should I change each weight? So a reference for this was made when we looked at maximum entropy Markov model, MEMMs, for chunking. So there you would recall that we had to deal with features and the weights of these features. So we actually had lambda values, which are feature weights, and the lambda values were changed by gradient descent or ascent algorithm. Okay, so the same idea here. We first decide on the error function at the outermost layer. So E is given as half into j equal to 1 to p, I equal to 1 to n, ti minus y square. What is the meaning of this? This requires referring to a neural network. So I have the neural network here, feed-forward neural network. This is the input, and all these are hidden layer neurons. There is this outermost layer where the results are obtained. Now at the outermost layer, I know the label values. Each neuron's value I know for any given input. So the if I is the index which is running over the neurons in the outermost layer, then Ti minus Oi. Ti is the target value which is expected at the ith neuron. Oi is the observed value at the ith neuron. Then Ti minus Oi is the measure of error. Now I have to add all these errors over these neurons. Now if the errors have signs, they can cancel each other and thereby give a false impression that there is no error. Therefore, we either take mod or we take the square of the difference. We take the square difference because square functions are differentiable. Mod values are discontinuous at 0, and therefore we take the square function. Now this square of the difference is a component of the error. Now I take the sum over the neurons. That is why we have sum square error. And I do the same thing for all input output patterns. That's why it is total sum square error. Okay, So that's how the error function is developed. It is called TSS, total sum square error. Square because ti minus y square, total sum because summed over all neurons, and total because total over all patterns. So this is the error function. It is also called the loss function. So the error function for the feed-forward neural network is half into, first of all, the inner sum ti minus y square over all possible I going from 1 to n neurons outermost layer. Then j going from 1 to p, j is the pattern number, and half is there as a mathematical convenience. Because I have to take derivatives, gradients means derivatives. When I take derivative, then this 2 will come down, and because of half, this 2 will get cancelled. Okay, so it's a mathematical convenience. So this is the total sum square error, also called the loss function. So Jyotsna, please add a slide called loss function slide. So loss and error are synonymous. Now there are competing loss functions. One of the most popular loss functions, other than total sum square, is the cross entropy loss. And cross entropy loss is more used, at least in NLP, than the total sum square error. Total sum square error is used, for example, in time series prediction, stock market prediction, any kind of situation where. But in NLP, entropy loss is more frequent. So Jyotsna, please give a slide on cross entropy loss, give the formula there, and also mention that this is used in NLP more than total sum square error. Another point to note here is that total sum square error is interesting from another point of view. Okay, it is actually a maximum likelihood estimate. Total sum square error is a maximum likelihood estimate if the input data obeys normal distribution. Okay, I'm just stating this result, not proving it. If the input data comes from a normal distribution, then the total sum square error is a maximum likelihood estimate. So Jyotsna, please write that also. Okay, so so this is the expression for error. Now we apply gradient descent on this. We are interested in finding out how the weight value WMN will change through gradient descent. Now N is the feeding neuron, M is the receiving neuron. N is the sending neuron, M is the receiving neuron. So the most important step in the discussion comes from the gradient descent rule. The change in weight is proportional to minus delta E delta WMN. Okay, so what does that mean? This means that if I initialize the WMN value, then at every iteration, I'll change WMN by delta WMN. And delta WMN will be nothing but a negative gradient of error with respect to WMN. And what is E? E is this total sum square error. Okay, which is taken as the square of the difference in target and observed value over all neurons over all patterns. Okay, so we have here delta WMN proportional to minus partial derivative of error with respect to WMN. Now we cannot anymore deal with the step function. Okay, the reason is that step function has discontinuity. It is not differentiable. Now partial derivative, which is required in gradient descent, requires differentiability. Now differentiability is possible only for continuous functions. So we introduce a continuous function for the input output of the neuron. So the function which is most popular is the sigmoid neuron. Okay, And sigmoid neuron has this continuous behavior. Its equation is 1 by 1 plus e to the power minus x. Sigmoid neuron's equation is 1 by 1 plus e to the power minus x. Okay, so the output function of sigma wixi. Now wixi is nothing but net input which arrives at the neuron, and we take partial derivative of the net of the output with respect to net, which will be the derivative of the sigmoid neuron. Okay, so we proceed, and we are interested in finding out the change at the jith weight parameter value. Here j is the destination neuron, I is the source neuron. Descent rule, change in weight is equal to minus of learning rate eta and partial derivative of error with respect to wji, the parameter we are interested in. Now there is a series of mathematical steps which I will go through line by line, but you will surely have to go back to the slides to look at the derivation. So now delta E delta wji is broken as delta E delta net j into delta net j delta wji, where net j is the input as the at the jth neuron, not layer, jth neuron. Okay. Okay. So ith neuron and jth neuron are connected by wji, and delta E delta wji is delta E delta net j into delta net j delta wji. What is net j? Net j is the net input at the jth neuron. Now we give a notation here. Delta E delta net j is denoted as minus delta j. Okay, this is a notation. So then delta wji is learning rate into delta j into delta net j delta wji. Now delta net j delta wji is nothing but OI. Okay, OI is the output from the feeding neuron. Why is it so? Because net j is nothing but sigma wji wji OI. Okay, summed over all inputs which are coming at jth neuron. Now wji is a single connection weight, so that affects only one term in that summation. Okay, and that affects only one term. So net j is summation of terms. So only that term which has wji remains, and the term which remains as a result of partial differentiation is OI, the output coming from the ith neuron. So change in weight is eta into delta j into OI. So you must develop an intuition for this expression. It is saying that the amount by which the connecting weight will change is the output from the source neuron, the learning rate, and an abstract quantity delta j at the destination neuron. Okay, so this is the formula for change of weight, and I cannot overemphasize the importance of this formula. This same formula is applicable throughout the deep neural network literature. Okay, so this is the formula which comes in different forms and different shapes and different contexts, but the underlying principle is same. The change in weight is a function of learning rate, the feeding neurons activity, and the error activity at the destination neuron. Okay, so this is a fundamental rule of any neural network based computation. Okay, anywhere you see a weight change rule, you can ultimately reduce it to this kind of expression: learning rate, error function at destination neuron, activity from the source neuron. Okay, so let's proceed. Backpropagation for the outermost layer. So can somebody verify you are looking at backpropagation for outermost layer? Somebody please.
Yes, sir.
Yeah. So now we are interested in delta j. Delta j is minus delta E delta net j. Okay, we are doing mathematical derivation, and now we are not thinking about any problem or intuition. We are simply doing rigorous mathematical operations. So delta E delta net J is delta E delta Oj into delta Oj delta net J. Again applying chain rule. So error is a function of the output from a neuron. Okay, and we are discussing only the outermost layer, not the hidden layer. Okay, so in the outermost layer, we find the error value. The error value is difference of target and output. Now delta E delta net J doesn't involve delta Oj, doesn't involve Oj output. So we introduce it through chain rule. So delta E delta Oj into delta Oj delta net J. Net J is the input at the jth layer, it will be jth neuron. So now error equal to 1 by 2 sigma p equal to 1 to m tp minus op square. So p is the pth neuron. Okay, 1 to m tp minus op. Now if I look at delta j, this is nothing but delta e delta oj is differentiation of this term tp minus op square, and there are m such terms, but only one term will remain because it is a partial derivative with respect to oj. So only that term which involves oj will remain. So if I take the derivative, 2 will come down and get cancelled with half. Minus also is obtained. So this is tj minus oj into oj into 1 minus oj. Where is oj into 1 minus oj coming from? oj delta not j is nothing but the derivative of the input output function of the neuron. O is the output, net is the input. So the function that transforms input to output, typically it is the sigmoid neuron for the neural network. So the function is sigmoid function. Sigmoid function is 1 by 1 plus e to the power minus x, y equal to 1 by 1 plus e to the power minus x. Okay, Jyotsna, please add the sigmoid function form. 1 by 1 plus e to the power minus x, and dy dx becomes y into 1 minus y. This you can verify for yourself, that the derivative of the sigmoid function is nothing but product of y and 1 minus y. Okay, and you can, this is interesting. If y is a probability value, probability of success, then 1 minus y is probability of failure. Okay, so you are multiplying probability of success by probability of failure if y is the probability value. That's interesting. And something like this happens in logistic regression. You will recall y into log of 1 minus y. And if you have y into log of 1 minus y, it is like an entropy component. Okay, so y into 1 minus y is probability of success into probability of failure. Y into log of 1 minus y is the entropy element. Okay, so these are so y and 1 minus y are interesting quantities. So what we have now is the change in weight is learning rate into tj minus oj into oj into 1 minus oj into oi. So let's remember this weight change for the outermost layer. So in the outermost layer of the neural network, each weight is changed by this quantity. What is the quantity? First of all, learning rate. Then tj minus oj is the difference from the target value of the observed value. This is like an error term. oj into 1 minus oj is the derivative of the sigmoid, and oi is the input arriving at the connection. So now you can analyze the behavior of this. So if tj minus oj is large, if there is large error, then the weight will change by large amount. If tj minus oj is small, if tj is equal to oj, then there will not be any change in weight. Another interesting observation is if oj is 0, then also there will not be any change in weight. If oj is 1, again there will not be any change in weight. Now sigmoid neuron, sigmoid function is bounded from 0 to 1 plus 1. 1 by 1 plus e to the power minus x. So this quantity reaches a value of 1 for x equal to infinity, and it reaches a value of 0 for x equal to minus infinity. Okay, so when the sigmoid function receives an input of plus infinity or minus infinity, that means very large positive value or very large negative value, then also the change in weight is negligible, small. This is called the saturation behavior. Again, Jyotsna, please write this down. This is called the saturation behavior. The neuron is now operating at the saturation region, either the negative saturation or the positive saturation. And the other quantity of interest is OI. So if the input value is 0, again the change in weight is 0. Okay, the weight doesn't change, input is 0. What is the physical significance of that? That means if the input received is 0, then why should the weight change? If the input received is 0, it is not contributing anything to the error. So why should the weight be penalized? Okay, the weight should not be penalized if the input is 0. And this is called the credit assignment problem. Okay, so credit assignment kicks in if OI is 0. If OJ is 0 or 1, then saturation kicks in. If OJ is equal to TJ, then the error becoming 0 is the influencing factor. In all these three cases, the change in weight is 0. So it is instructive for you to note the various conditions under which the weight will not undergo any change. Okay, so this is the picture for the outermost layer. Okay, this is what is in the outermost layer. Yeah. Yeah.
So this error is summing over patterns or number of neurons?
Yeah, I think there is a bit of change of notation. This error is over the number of neurons. Okay. Now, if I take this expression over all patterns also, then the question that arises is that in weight should be posted at what instance? After I have given an input-output pattern, I can find out the change in weight that is required for that pair, that input-output pair. So should I incorporate that change immediately or not? Or should I wait for all the patterns to be over? So if all the patterns are seen and the change in weight values are accumulated and finally posted, this is called batch learning. Again, just I'm sorry, this point again has to be mentioned in the slide. Batch learning is when we have seen all the input output pairs, accumulated all the changes, and finally posted it on the weight. So this is an example of batch learning, and one run of the whole input output set is called an epoch. Okay, one run of the whole input output is called an epoch. So if you post the change after an epoch, it is called batch learning, which is also called offline learning for some reason. And if you post the change at every input output pattern, it is called incremental learning or online learning. Okay, so these are the two different modes of weight change. But in this current case, the sigma is over the number of neurons. Okay, so now we come to now we come to what should we do for the hidden layer neuron. Okay, for the hidden layer neuron. The problem with hidden layer neurons is that I do not have the t values here. Okay, the t values were incorporated after differentiation of the error function. Now t values are not available for the hidden layer neurons. So how do I incorporate the weight changes here, and what is the change value after all? Okay, so let me just show you the mathematics, but we will elaborate it in the next class. The change in weight again remains to be the general expression eta into delta j oi. Delta J is defined as minus delta E delta net J. The derivative of the error with respect to the net input in the jth neuron. Now the jth is not the outermost layer's neuron. It is a hidden neuron. Remember that. So again, I apply chain rule and get delta E delta Oj into delta Oj delta net J. This is same as the process applied for outermost neurons. And I get minus delta E delta Oj into 1 minus Oj. Delta Oj delta net J is nothing but derivative of the sigmoid, which becomes output into 1 minus output. The problem now comes with delta E delta Oj. For outermost layer, E is a direct function of Oj. For hidden layer neurons, E is not directly affected by Oj, because Oj is output of a hidden neuron. Oj is not directly contributing to the error expression. So here comes probably a very clever trick. This is the foundation for backpropagation algorithm. It was discovered independently in 1972 by Lecture-35 and in 1984 by McClelland and Rumelhart. Okay, just now again you have some work. So independently discovered in 1972 by Lecture in France and McClelland and Rumelhart in 1984 in USA in MIT. But people say that just like Viterbi algorithm was discovered in many parts of the world, in many disciplines, the idea of backpropagation made its appearance almost in the same time range at many places of the world and across many different applications. So therefore you have this adage that when the time comes for an idea, the idea makes its appearance at multiple places. Okay, so this is the backpropagation rule. I convert delta E delta Oj into delta E delta net K into delta net K delta Oj. What is net K? Net K is the next layer's neuron. K is the next layer's neuron. Next layer is closer to the outermost layer. So Oj doesn't feed E directly, but Oj feeds the net input in the next higher layer. Okay, and net in turn influences the output of this layer, which again influences the next higher layer. So this way a kind of chain reaction happens. And if you can capture the chain reaction by means of mathematical modeling, then you have a procedure in hand. So delta E delta Oj is converted into delta E delta net K into delta net K delta Oj. Now Oj feeds into many neurons, in fact all neurons in the next layer. It is a completely connected feed-forward network. So it feeds into all neurons in the next layer. That's why you have to sum over all neurons in the next layer. So this is the sum, and the Oj into 1 minus Oj comes from derivative of the sigmoid. Now delta E delta net K is again nothing but delta K, which is the error function at the kth layer, and delta net K delta Oj is nothing but Wkj, because net K is a function of Oj multiplied by the connection weight Wkj. So notice that you now have a recursive expression in terms of delta again. So delta J is a function of delta K, and delta K is nothing but the next higher layer's quantity. So the boundary condition will be the outermost layer where delta K is known in terms of target minus output value. Okay, so this is the weight change rule, and I have the weight change rule as Wkj delta K into derivative of the sigmoid. Wkj into delta K is like a weighted sum of delta K values. Delta K values are error expressions. So this is the error backpropagation expression, and that's why this is called error backpropagation algorithm. The thing to note is the way invoked. Okay, delta j is recursively a function of delta k. Delta k is recursively a function of delta k plus 1, where k plus 1 is the next higher layer closer to the outermost layer. So this is a very, very instructive, very beautiful algorithm in AI after perceptron algorithm, or in the same class as perceptron algorithm. So again, I'll very strongly recommend, Satyam put this as an exercise, that you implement backpropagation on your own. There are many tools available, including MATLAB, and I think Python also has a library for backpropagation. But you implement it yourself and run it on XOR. Implementation is hardly anything. It is just two weight change rules, layer, one for hidden layer. And these are simply two equations. So maybe 15-20 lines of code to arrange for all kinds of variables, declarations, and initialization, etc. will be required. But otherwise, it is a very simple algorithm to code. So the exercise you have is code backpropagation algorithm. Please put it in the slides also, Jyotsna. Put implement backpropagation, run it on XOR, and see if it converges. Okay, for the given input-output pattern. So for XOR, for 0, 1, you should get 0. For 1, 1, you should get 0. So those 4 patterns will have to be trained and find the correct weight values. Also observe what is being computed at the hidden layer. So this is a very useful exercise to do. So now let me, I think it is almost now time for question answer, but let me very quickly show you an application which is backpropagation, and then we can take it up in the next week's lectures. So an application in medical domain. So we are creating an expert system for skin disease diagnosis. There is bumpiness and scaliness of skin, okay, mostly for symptom gathering and for developing diagnosis skill, and no replacing doctor's diagnosis. So doctors are not being replaced. So this is a skin specialist job. There is bumpiness and scaliness of the skin, and you have to diagnose what is the disease of the skin. Now, a feed-forward neural network is used for this. So look at this. There are multiple layers. There is one hidden layer and there is one output layer. In the output layer, you have the disease decisions. Psoriasis is a particular disease. Dermatophytosis is another disease. Seborrheic dermatitis node. So these are different diseases of the skin, and each neuron becoming 1 or 0 indicates that disease's presence or absence. There is a hidden layer which does internal representation, and the symptoms are presented in the input layer. So duration of the lesion, number of weeks, minimal itching, positive KOH test, lesions located in the feet, minimal increase in pigmentation, positive test for pseudo, phi and spores, bias. So all these things are given by the doctors. Okay, so these input features are really the doctor's business. Computer scientists would not know about this. Similarly, doctors will also give the names of the diseases here. After that, designing this neural network is a deep learning engineer's job. And what happens in this internal layer? What is each neuron doing? That's a very interesting medical question. So is it grouping? Is it clustering a set of symptoms? Is it indicating some intermediate disease stage? That's a very interesting question. So I'll stop with that, and we'll continue with backpropagation discussion in the next week, and then slowly move to application of feed-forward network, or CNN. CNN is a logical extension to feed-forward network to deep. Okay, questions now?
Sir, I'll begin with the questions which are left from the previous class.
Right.
The first one is by Saurabh. Can we get the number of different parse trees from the table drawn in CYK algorithm without drawing the actual trees? I mean, there are some cells with more than one possible combinations, but their multiplication doesn't seem to work.
So can you retrieve the parse tree from the CYK table? Is that the question?
Yes, sir.
Okay. Yes, you can. Yes, from the, so you want the algorithm for doing that. So how you follow the back pointers and retrieve all the parse trees. Is that your question?
Sir, I tried like multiplying all those numbers. So for some cells, we have like 3 combinations at that particular node. And then for some other, at the end, I just multiplied all those numbers with more than one sort of combinations possible. But that gives a greater number than the possible number of trees.
Oh, you're talking about the alpha beta pruning. Alpha beta, sorry,
No,
inside
sir.
outside algorithm.
For the number of parse trees only, sir. I drew that table. And for
Uh,
some columns, like we have multiple options, right? We can combine 2 cells, but like there are multiple options at that cell. Maybe I'll do the mathematics and then post you there.
yeah, and then you can set up a meeting with me, send a mail, and
Yeah.
we can have an e-meeting to discuss.
Yeah. Pranav is asking about the mission. The lady plus S ladies in the question made identification of the stem confusing. I thought lady was stem because of that example.
So we
So
discussed it
basically,
last time.
yeah. But, okay. Anyways, I'll move on because this is just I believe this is just an opinion and less of a question. Okay.
Yeah.
So Varad asks, while talking about perceptron, is it implicitly understood that the step function is being used as an activation function?
Yes. Yes. Perceptron uses step function. Yes.
So that was the last question. We have taken previous classes questions, and Saurav's question is the only one remaining. So maybe without switching the view to full screen, if you can just move over the slides, Saurav would be able to find
No,
the
but today,
particular.
today is there any question?
This is today's question.
Okay. E versus W bar surface is a complex surface in the space defined by weights WH. W bar is the weight vector. So in XOR function, there are 4 weights from input to hidden and 2 weights from hidden to output. So there are 6 weight values. So it is a 6 component vector. So W bar is the complete weight vector for the whole neural network. Now, if we take a multi-dimensional surface where each dimension is one of the weight values, and E is the error resulting from a pattern. Okay, then for different values of the weight, okay, different values of the weight, you will get different E values. Now, if you plot E versus the weight vector, this will be a very, very complex surface. Okay, it is impossible to visualize this. So minus delta A delta W Mn gives the direction in which the movement of the operating point, movement of the operating point, 5 minute ke baad. Movement of the operating point ensures reduction in weight. So gradient descent algorithm is a greedy algorithm. It always reduces the weight because of this quantity minus delta A delta WMN. So it moves in the direction of the negative gradient and thereby decreases the error value. So if the function is rising at a point or falling at a point, whatever be the sign of the gradient, the error value will always decrease if you follow gradient descent rule.
Yeah. Thank you.
That you should verify yourself. Okay, so if it is increasing, if it is a positive gradient, then the weight change will be negative. If you have a falling curve, then the weight change will be positive. That is ensured by this minus delta A delta WM. Okay. Okay.
Sir, that was it.
That is it. Okay. So I guess all of you are now making progress with your project and assignments. We'll follow the timeline which has been announced in the class. And do please keep monitoring all the announcements which are posted in Moodle and MS Teams.
Sir, we have already given them the timeline that we discussed. They already know when all the next evaluations and the next quizzes are going to happen.
Correct.
The only thing I believe remains is a mistake on the TA's part, that we have not yet completely evaluated the quiz in midterm, and we apologize for that. But we will very soon finish it and get back to you with the marks. Okay, guys.
The complete model answer has been given now.
Yes.
Given along with the derivation for.
Yeah.
Okay, where left to right and right to left can give rise to equivalent result. So that you should see. Okay.